Okay, welcome to the projectile motion analysis Excel application. So I just thought I'd show you guys a quick video around how to make use of this in order to get a better understanding of all the intricacies involved in projectile motion. And there's numerous things to assess and analyze. So from the theory side of things, we realize that there are a couple of things that affect projectile motion and how far it goes, how high it travels, how much time it tends to spend in the air, so on and so forth. So with this application, it'll allow you to play around with release height, landing height, release velocity, release angle, and even a little bit later on to kind of assess the effects of air resistance in terms of air drag on the motion of a projectile. So there's a couple of things in this application that we can kind of start with in terms of our analysis. The first one here, you see that there's a red line that will correlate with whatever data we put in here in terms of what we've called the red projectile. So you'll notice that there's a release velocity that I can change, there's a release angle that I can change, and there's a release height that I can change. The release height at the moment is just set at 0. I can also include the velocity vector just to kind of give an indication of the angle and magnitude with which this projectile tends to be released. I've got this button over here that allows you to go backwards and forwards in time. So if I press backwards, you can see here how we go backwards in time, and if I press forwards here, we can kind of just trace how the projectile tends to move throughout time, and the graph will automatically update all of that information. I can switch the velocity vector off, and then we just see our normal graph. So that's just to give you an indication of the release angle and magnitude of the release velocity. Other things that may be important is this live data value tab. It kind of just shows you at any point in time what the time is, what the range is in the x direction, what the height is in the y direction, what the velocity in the x direction is at any point in time, and the velocity in the y direction is at any point in time. So what we can see here is if I'm going back in time, these values tend to update automatically. I've allowed it to go up by every 0.1 of a second. So you can see here that as the projectile is being launched at the first 1/100th of a second, it's traveled 1.69 meters horizontally and 1.01 meters vertically. Its velocity initially, the release velocity was 20, but even 0.01 of a second into its flight time, that release velocity has already started changing. Remember, it's subdivided into x and y components. So that's kind of what we're delineating over here. So if I go a little bit further back to its initial point in time, before it is even launched, you can see here that there's already an x and a y component at the instant of release. The moment that it starts traveling, you'll start seeing that the y component starts to decrease. And you may be wanting to ask yourself, well, why is that the case? So think about the net forces acting on this projectile at any instant in time. Right now we are ignoring air resistance, so it's only gravity that tends to be affecting it, and gravity tends to pull something down. In other words, it's slowing it down, and that's why this particular graph is here. It shows you what the vertical velocity and horizontal velocity is at any point in time. You will notice that the horizontal velocity is not changing, so when I go forward or backwards in time, it's the exact same value. But the y component does change. It tends to be decreasing. And what do we know about the peak? Or at the peak of its motion, the vertical velocity should be 0, right? And that's what we'll see here. Is you can see it's gotten really, really small, and then all of a sudden it changes. So somewhere in between here, it reached a vertical velocity of 0. And in terms of height, or the point in time when that happened, you can see here that we've been at the 5.7251 meter instance. So we're quite close here in terms of where we are along that point in time. And then as I keep going forward, now we'll have a velocity that's just changing in magnitude again. It's increasing because of this change in direction. Okay, so you can see here that the vertical velocity component tends to go bigger and bigger and bigger and bigger. You have options to switch that off. So if I want to switch the horizontal velocity vector off, and you just want to have a look at the vertical vector, you can do that. If you want to swap it around and just look at the horizontal component and switch the vertical component off, you can see that, and ultimately you'll see that these are unchanged. And if you want to look at both of them at the same time, you can do that too. Okay, so you can see here, this is the live data as I mentioned, and this is the projected value. So once we've assessed and analyzed the entire projectile motion, this is the summary of the values that we'll see. So the total flight time is 2.16, the maximum height is 5.71, and the total range is 36.64. Okay. It will change and update automatically depending on the values that I put in. So here, if I put in 30, you would see that that makes a difference in terms of where a projectile would be at a given point in time, and it will spend more time in the air, right? If I change the angle, so I keep the speed the same and maybe I change it to 50, you will see that that tends to affect where it would be at any given point in time. And I can assess and analyze all of that again. Again, these are the live data values, these are the projected values from beginning to end. Okay, so it might be a bit cumbersome to keep changing this to see what the effects are, so I've allowed for more numerous projectiles to be added in, specifically 2 more. So in, let's say, an instance where I want to keep either value unchanged and assess the effect of another value, let's say, for example, keep the speed the same, but start changing the angle. So if I keep the speed the same as the first one, I will change that in here. And I want to play around with an angle, so let me go 60 degrees. And in this case, I would keep the speed the same, and I go, let's say, 10 degrees below, so make this 40 degrees. And I want to include these in my graphical analysis. So I just select yes. And you'll see here that at any given, at the same instant in time, right, this same instant in time, which tends to be 4.6 seconds, where the different projectiles would be. The red projectile has almost landed. The purple projectile would have landed and continued to travel, and the green projectile would still be in the air at the same instant in time, right? We can see here again the summary would tell us what the differences are. The red projectile would have had a total time in air of 4.68 seconds. Green projectile would have spent more time in the air, and the purple projectile would have landed already, right? And we can see differences in height and differences in range. So it seems here that the optimal distance seems to be a higher angle, and interestingly enough, the purple and the red would have achieved the same range. Right, and what you'll see, I'll leave it to you guys to establish why that is the case. But think of some optimal angle and distances above or below that angle, what the effects will tend to be, right? So what's quite interesting is that at an optimal angle of 45 degrees, any equal degrees above or below will result in the same distance. So 45 is our optimum. Note here that 50 and 40 is 5 degrees above and below, and it's one of the reasons why this would end up in the exact same position. Okay. And any angle beyond 50 degrees would lead to sub-optimal ranges. So if we're assessing projectile motion, what is the optimal angle and why would that lead to the optimum distance? Note, if we had to keep the angle the same, let's still keep this at 30 and change the speeds to, let's say, 10 meters per second above and 10 meters per second below, how we would have again differences in terms of range, right? So if I play this just a little bit backwards, you see that when the purple one would land, the red and green would still be in the air. We see here that there's differences in time again, differences in max height again, and significant or substantial differences in range, right? So you'll notice that the green has the highest velocity and it achieves significantly greater range even at the same angle, right? And then ultimately you can play around with release heights. So if we had to keep the speed and the angle the same, but change the release height, and maybe make that one 0. So let's make that 30, and let's make that 30. Right, they should have the same kind of motion, but the only thing that we've changed now is the release height. And notice that there again will be differences in time, maximum height, and range. Okay. If you want to change the landing height, in essence, all you'll do here is change this to a negative value. So we'll put -2, or let me just make it a little bit more obvious, -10. And I'll make the angle a little steeper, make it 50, and then I'll switch these off just so we can assess that in isolation. Alright, so now we have a release height that is lower than the ultimate landing height, right? So in essence, what we can see here, again, if I play it forward in time, this 0 line is ultimately where we are calculating our landing from. So let's compare that to when the release height would be 0, and I'll just include that. And we can see here that there's a difference, right? Not a significant difference. This, if an object is released and lands at the same height, relative if it was released from a height lower than what it lands, how that would have an effect in terms of range and height. Okay. So again, we could play around with a couple of different parameters to see what the effect of release height and landing height is on the ultimate range of a projectile. Again, if we had to keep the release height the same and play around with different angles, what would the effect on range be? Because there's something that the theory tells us in terms of release height and landing height and the effect on range, depending on the discrepancies between those values. Okay, let's look at one more aspect of the analysis. I'm going to, well, let me just switch that off and that off. I just want to look at this in isolation, and I'll look at it from 0. So what does the theory tell us about projectile motion? So there are a couple of things. If we tend to ignore air resistance, it says that there are no horizontal accelerations or decelerations, so nothing's making this projectile go further or shorter. So in essence, its horizontal velocity at the beginning should equal its horizontal velocity at the end, right? We can see that in the length of these horizontal velocity vectors here, they're all the same, but we can try and prove that with some graphical analysis, right? So first of all, relative to, if I had to plot time on the x-axis, you would notice that at any instant in time this projectile is a little bit further horizontally, and that's exactly what we see here. So that if I have time on the x-axis and its horizontal position on the y-axis, at any instant in time the projectile is some constant value further, right? So at 1 second it's about 20 meters, at 2 seconds it's about 40 meters, at 3 seconds it's close to 60 meters, so on and so forth. Right, it's predictable. There's nothing slowing it up or speeding it down. Speeding it up or slowing it down, sorry. So if we had to look at it, before I get to that, what you guys should remember from class is that if I had to take the slope of a position versus time graph, I should get the velocity. So since this is increasing at a constant rate, if I took the slope at any point in time, I should get the same velocity. It's unchanging. So if I took the velocity versus time graph, you'll see here that it's at a constant value, right? It's not changing at any instant in time. And that again matches the theory where we say that nothing is slowing it down or speeding it up. It's constant, it's unchanging. In terms of its acceleration, its horizontal acceleration, we said there was nothing slowing it down or speeding it up. So you should see that when you plot the acceleration versus time graph, it should be 0. Remember that when you take the slope of a constant, you will get 0. So again, that matches up. What about the vertical motion? So if I had to look at the vertical position at any instant in time, remember this is time now, not position, and this is its vertical position. So at any instant in time, it's going up initially, it reaches some maximum value, and then it goes down and ends up at the same position from where it was released. Okay. What do you think would happen in terms of its vertical velocity? So remember that the only thing acting on it, on a projectile, when it's in the air, is the downwards acceleration of gravity, right? That's what we can see here. The vertical velocity is some high value, and then it becomes smaller and smaller and smaller and smaller, decreases to 0, and then it becomes bigger and bigger and bigger and bigger in the negative direction. So we should see a downward sloping velocity time curve, and that's what we see here. It's some bigger value. It gets smaller and smaller and smaller over time, reaches 0, and then it gets bigger and bigger and bigger as time increases, and we'll have some velocity, some larger downwards velocity towards the end again. Okay, remember the negative doesn't mean that it's smaller, it just indicates the change in direction, right? It went up and then it went down. In terms of the acceleration, so remember that the only acceleration it's experiencing is the downward acceleration of gravity. Downward acceleration of gravity is negative 9.81, and that's exactly what we see here, and it's constant. It doesn't change throughout its entire flight path. Okay, so useful analysis. It's matching all the theory that we've learned so far. So the last point of departure would be to see what the change in this parabolic flight path would be in the presence of air resistance or drag. So if I include that option, you can see here it's denoted by this blue graph, right? And you can see here that not only does it reach a lower height, but also a shorter distance in the presence of air resistance. We can see here how much different that would be. So in the presence of drag, the range would almost be 9.6 meters shorter at this speed and at that angle. The height, remember this is live data, so it's showing me where it is at this point in time. If I want to play it a little bit further backwards and kind of get an idea of its maximum height, so kind of here, you would see here that the height of the red line is about 26.7 and the height of the blue line is about 25. So it's about a 1.7 meters shorter in terms of maximum height. And we saw the effect then on range as well, right? You'll also notice significant differences between the vertical and horizontal velocities. Okay, so you'll notice that the horizontal and vertical velocities respectively here. So the horizontal velocity is significantly less because now there is something that is blowing it backwards. So it's 16 versus 19. And also the vertical velocity is different. It's actually slightly faster at this instant in time because it's had some more time to travel down. This one's still in the air relative to that point in time. So it'll be interesting to see what those differences are in the presence of air resistance. But it does have a significant effect. And remember that the equation for drag shows that the effect of drag is proportional to velocity squared. So if I increase this number even more, let's make it even more significant, 80, you will see that the effect will be even more pronounced. So if I continue to play this, the faster the projectile tends to travel, the more the drag will have an effect on it. Okay, so you can see here at this point in time, its range in the presence of drag is 309 versus 514 in the presence of no drag. So you'll see that the no drag projectile would still continue up to some maximum distance of approximately 642 meters, right? So that is significantly different. Okay, so it's one of the reasons why, yes, we can ignore drag in instances when projectiles are moving at slower velocities. So if I decrease this to something silly like 10 and I play it backwards, sorry, it does take a little bit of time because I do only increase it and decrease it by increments of 0.1 of a second. You'll notice that with slower velocities the discrepancies are not so substantial, right? In this instance the range is a mere 16 centimeters off each other, right? It's really almost insignificant. No real changes in height, no real significant changes in vertical or horizontal velocities, right? But it's as the speed tends to increase to faster moving projectiles that those discrepancies become more noticeable. And it's one of the reasons why later on we can actually not ignore drag. But now, the point of this was just to introduce you guys on how to use this, and how to manipulate the various variables and where to get the information from that you ultimately need for your prac. So I hope that makes sense. If you guys still get stuck, please feel free to ask me any questions in class. Alright, good luck.